Hello. Let me see what's going on here. All right. Nice turnout. Good. Hope everyone's doing well. If you got questions, you can chime in or you can type them in the chat. I've got them open. I'm gonna start sharing my screen to you. I'm not muted. Nope. If you can't hear me, let me know. Shares. All right, so I just wanted to point out a couple things because I posted a number of things that will keep you busy for the next couple of days and month, just so you're aware of it. So under modules, the group project, it's right up at the top. So I'll be working on that tonight. I'm just trying to give everyone a chance to respond to that poll so that I can make that group as those groups the best way I can. And I just thought the most important thing for me is, I mean, if someone's honestly dropping the course, not that I'm encouraging it, but if you are dropping the course, it's beneficial for me to know so that I can try and make the group a group that doesn't include you. So it's not a group that just doesn't have enough people, or that I have to reshuffle people around after I find out. All right. Let's see. All right, so then also right here, I posted solutions to the Extreme Homework quiz. We're gonna go over it right now anyway, but that's gonna be the link I'm gonna use to even show you the pictures and stuff. One quiz on Friday. First question, right, but not in the format. All right, Dave, you should just email me, so then I'll take a look. Oh,
okay.
Oh, it's private too. I'm sorry. That's what I doesn't even see. Yeah, email me.
Gotcha.
Right. So
I'll screenshot my answer and I'll send it to you.
Yeah, that helps. Yeah, that will help. Thank you. Homework number 5 is the new thing that I posted here outside of those solutions. We'll go over the solutions shortly. But homework 5, just so you see, you have all the way till 2 Fridays. So not this Friday, but the next Friday after that to submit it. 5 problems. They're focusing on the things that we've been working on the extremist stuff that we've been working on and the stuff that we're going to do today. That's all. There's also some new material in there in terms of a biological application of this. But the theorems that we're using, we've already seen in terms of finding critical values and things like that. But it will be good for those of you not being math majors, right? Being science majors. You're holding tutoring. I'm not holding tutoring sessions. I do have office hours where I'm free to, answer questions and go over stuff with you. The email that I sent to everyone, there's one of the graduate assistants is having, there's a graduate assistant that's doing tutoring. I think I sent that email out to the class. But I'm 9 o'clock Monday, Tuesday, and Thursdays. I'm online in the morning on this link here, answering any questions that you've got. So you can definitely stop by for that as well. If you want to call it, I don't know if you want to call it tutoring or not, but I'm here to help and answer questions and show you additional things and stuff like that. All right, so your homework 5 though, there's a reading that goes with 2 of the problems, so that's what this reading is. But start with the homework assignment itself. It's got 5 problems, and you can start working on those. And then you'll submit it through here by April 7th. All right.
Was homework for the homework quiz?
Yeah, we'll call that one homework 4. I skipped it just so that we have a specific, just keeping count of it.
Okay.
But it's going to be on similar material. It just isn't going to be, it's not as easy, I'd say.
All right.
All right. I know some of you may disagree that this last one that homework was easy or not, but let's take a look at that now. All right, so quizzes. All right. Aurora, what's wrong, baby? You want to come out of here? You want to come out? Sit on my lap? All right, so here is the quiz. Let's preview it. All right, so this first question, I honestly think some of you just made a very simple mistake. You didn't read this correctly. Because I think you probably all know how to do this type of problem. It says the first derivative of f is given. This is the first derivative. I'm not asking you to calculate it. I gave you the first derivative. And then it's saying how many critical values does f have on this open interval from 0 to 10. So my assumption is you're using Desmos or a calculator. And so you should plug this into the calculator as is. And you can do this two different ways. Let me open this up for you. So problem one. So the way that I did it, but I saw a student did it another way. I could tell through one of the questions they sent me. So this is the way I did it. I plotted the function as is over the interval 0 to 10. And so this is the derivative. So we want to know when does the derivative equal 0, because that's when there's a critical value. So we can visually observe these answers. There's one right there. Okay, there's one right here, and there's one right here. This one, it looks, is there one there or not? Well, you just zoom in. No, there isn't. There's no 0 there. So there's 3. You just counted them right there. 1, here's your second one, and here's your third one. But that is the function I gave you was the derivative function that you would have set equal to 0. And then I saw some other students had taken, instead of setting it up like this, what they did was they just took this and then set it equal to 0. And that you should do that. That's another way of doing it. And then you can visually see it's easier to see that there's only 3. I just saw.
So there were 3.
Yeah, the answer was 3.
Oh, okay.
Right. So I didn't take the derivative of this to see what you guys saw. I'm assuming that a lot of you took the derivative of this, and that's where you went wrong. I saw a lot of answers of 0. So I don't know what that derivative was. Maybe you were right about that. But this is what I was looking for. All right, number 2. Let f be the function defined by this. Okay, I gave you the answer. I just totally botched that one up. So that's the answer right there. But you should check it and confirm it. But it's saying, what is the critical value of f? Take the derivative. That's the way that you'd solve this. But even before that, graph it, because you have plenty of time, at least in my belief, you have plenty of time on this quiz. Give you a lot of time. So you could graph this to see where it exists about. So let me get rid of this stuff first. So this is, here we go. Okay. So this is the graph of natural log of x over x. It goes up, and then it either levels out and stays perfectly horizontal, or it's decreasing slowly. We go further and further down, we can see that it's decreasing, right? Because there's a little space in there, there's a little gap, you can zoom in and see it clearer. So there is a maximum. It's not easy to see where it is. So we visually can know that there's a maximum, but we visually also can't figure out where the heck it is. I mean, I can say it's less than 5. I can confidently say that I know it would be less than 5. So then what do? You got to take the derivative. And when you take the derivative, which we've done this, I think this was even an exam question, you get 1 minus the natural log of x over x squared. So I said that equal to 0 and find that, but it's not visually obvious. So what if I just set it equal to 0 like that? It will draw a line exactly where that's happening at. So this is where this is equal to 0. I'm keeping the original function plotted so that I can see relative to that function, where is that maximum happening? So it is happening there. It's very, very slight, and it's not very obvious. But that's where that is. So then what is it? Well, you got to solve this. You've got this fraction is equal to 0. So multiply both sides of the equation by x squared. So now you have 1 minus the natural log of x is equal to 0. Bring natural log of x to the other side. So this statement here is truly the statement natural log of x is equal to 1. Well, where is that? That's at b. natural log of E is equal to 1. So that's how you would go about solving that. Just one more. Yes, this was the multiple choice, Connor. This was the multiple choice question. All right, so that's why the answer is E in this case, and you can see when I plot this on it, see E and this equal to 0 are the same thing. So that's the answer to problem 2, and then problem 3 is directly related. It says, what is that maximum value? So we know that it occurs when X is equal to E, but what is it? And so this is, I really feel like I gave you number 2 and 3, because by having number 2, you should have gotten number 3 correct. Because if E is that location, then you plug it in. So then you get the natural log, f of E is equal to the natural log of E over E. And the natural log of E is 1. So that's 1 over E. So that's the answer, 1 over E. So this is, I mean, and here's the, I mean, why these questions are good in my perspective is because this is a question that, you know, you can use your calculator, but it's still just, this isn't a numerical answer. It's 1 over E. Your calculator most likely isn't going to tell you that. So you still need your calculator to understand and see this, but you still also have to do some hand, you know, a little bit of thinking without just, you know, writing down numbers that your calculator is spitting out. All right, number 4. Let f be the function given by this. What is the maximum value of f on this interval? You see, now if it's me, again, the first thing I'm doing is I'm going to plot this because I know I'm going to have work to do, but why not? There's no rules told to you specifically that you shouldn't plot this. So take a look, because your eyes are going to tell you a lot of information about this problem, and then confirm it with the math later on. So problem 4. So when we look at this graph, and this one here, it's not restricted. The problem does have it restricted to 0 to 6. So I need to restrict this 0 to 6, so 0 less than or equal to x less than or equal to 6. It is a closed interval, so the endpoints are included. But when we look at this graph, I mean 0 through 6, so here's 20. So I'm not seeing it come up at all. I mean, I can scroll down and see what happened. Oh, there we go. It goes down and then it comes up a little bit. Well, what was the question again? Where is the maximum value of f, right? What is the maximum value? Oh, what is the maximum value? So they want to know the actual output itself. So where is that? We can visually, it's right here. It looks like it's at 0. And so when I go ahead and solve this, I can take the derivative, find the critical values, the critical value that we want to know, or I mean, actually, I mean, to show the work, that's what you would do, right? Find those critical values, do the first derivative test the endpoints of your domain, and then from there, but in this problem, because we can visually see it's happening at 0, plug it in. Plug 0 into P, and you're going to get out what the largest value is on that interval, because we know where it's happening at. We just need to see what is that value. So I plug 0 in, and I happen to get 0 back out. So the largest value occurs when x is equal to 0, and that value is 0 on this specific interval of 0 to 6. We look at the whole function, it might be a totally different answer. And we're going to look at this type of concept more today so that we're getting even better with that. And then number 5, so let this be a differentiable function on this domain 0 through 5, and then we're told about its derivative. On the interval 0 through 1, your function is decreasing, and then it gets to 2, 3, and starts to increase. We just found a local minimum. After, at some point at 3, it now switches back over to being negative. And then it goes down. And so we just found a local maximum up here. And then again at 3, this time at x is, sorry, at 2 we switched, and then 3 we're going to switch again. And so now we start heading back up again. It's positive now. And so we just found another local minimum. Doesn't switch again. So it went down, and up. So you got 2 local mins and then 1 maximum. That's the way you should think about that problem. So here, yeah, this answer right here has 2 local minimums and 1 local max. I'm going to move on to the other material. If you have questions about this stuff, you shoot me an email. I mean, I can go over any of these things in more detail. Is she out here? Here, you want to get her? 1 second, guys. Sure. Good. You're on my screen. Okay. You all right? Okay. You're going to have to come and get her, huh? Sorry about that. I see. What? Can't see anything. All right. So now onto the content. All right. So we're going to do global. This is section 3. You're not going to like this, please.
Why?
Because you're not as smart.
What is that? Tell me what is that?
All right. So we're going to focus in on relative max and mins and the global maxes and mins, and we're going to look at how we can start to think about certain things on specific types of closed sets. So there's an important theorem that we get from here. So let's just start with the theorem itself. Yeah, I'm going to put you down, okay? Please.
What kind of word is that?
It's seltzer water. You're not going to like it. Okay?
Oh.
All right? Oh, sorry. Okay. All right, so let's start with the extreme value theorem. So if f is a continuous function and we're only talking about a closed interval, this is a requirement, it's got to be a closed interval from A to B, then f attains both an absolute minimum and an absolute maximum on that interval. So that's, we've seen functions where there's no absolute minimum or absolute maximum, right, on open intervals. There's always been those open intervals where you can't approach that, you can approach that point, but because you can't actually get to it, we've seen that there's no absolutes sometimes. We saw it with the x squared example and some things like that. Hold on a second. Xavier, go outside and play. You're gonna have to wait, okay? Let them inside and lock the door, okay? All right. So this extreme value theorem is specific only to closed intervals, okay? So it says that if we have a closed interval and a function is continuous, it definitely has a maximum, absolute max and an absolute minimum. And because it's got that, there's only 2 locations where it could happen at. It could happen at a critical value, and it can happen at an endpoint, and that's it. All right. So we're going to look at problems that are specifically closed intervals, especially useful problems, and we'll be able to get a lot of information from that pretty easily too. So let's go to this problem here. They start with this one before they introduce that theorem, but let's try it out here. You've got this function. This is going to be similar to what you're going to see on your homework. G of x equals 1. It's cubic, right? And we want to find all the critical values of g within this specific interval, so -2 to 3. So you would take the derivative. Let me set this up in Word, and then we'll go about, I'll switch over so that you can see that, because you don't need to see the problem written out anymore. Once I've got that. Let me switch over now. All right, so now I'm sharing Word document. If I'm not, let me know. So we've got f of x is equal to 1/3 x cubed minus 2x plus 2. And then we want to consider its derivative. So f prime, because we're looking for its critical value, so f prime of x, that's just x squared, right? You take your 3, multiply it by 1/3, and drop down the index by 1, and then that's minus 2, and then your other 2 turns into 0. So that's your derivative, which is great because it's nice and easy. And we set that derivative equal to 0 and solve. And so x is equal to plus or minus, what is it? Yeah, plus minus, there we go. Plus or minus the square root of 2. Right, bringing it to the other side, take the square root of both sides. So that's your critical values over for the entire function. But this function, the problem, not this function, but the problem itself said that we are only considering the interval from -2 to -3. So -2 less than or equal to x is less than or equal to negative, no, positive 3. Yeah, makes sense. There we go. All right, so that's the interval that we're working on. And again, just as a reminder, that's the same thing as saying -2, 3, right? Using interval notation. So we've got this closed interval. The extreme value theorem tells us there's definitely an absolute max or an absolute min. And what we know is that it's got to occur at a critical value or it's got to occur at an endpoint. So great. So let's write out the critical values that matter to us. There's only one, right? Critical value that is inside the interval from negative, actually, where is negative square root of 2? What am I saying? There's both of them are in there. Negative square root of 2 is both, yeah, so they're both in there. So we have 2 critical values, and then we have 2 endpoints. One endpoint is x is equal to -2, and the other endpoint is x is equal to +3. So if we're just looking for the absolute max and mins, we actually don't have to do the first derivative test. There's a faster way, because you're going to have to do this basically anyway, which is plug them all into the function and see which one's largest, see which one's smallest. You know that they have to happen there, and so just analyze those outputs. So that's what we'll do. We'll calculate the following things that you want to calculate would be the f of the square root of 2. You want to calculate f of negative square root of 2. F of -2, and f of 3. And we're going to literally just look at all those values. So f of 3 is 9 minus 2, which is 7. F of -2 is positive 4 minus 2, so that's 2. F of negative square root of 2 is positive 2, and that's minus 2 is 0. And f of positive square root of 2 is 4 minus 2. So, no, so square root of 2 squared, so that's 2 minus 2, which is 0 as well. We can see our absolute maxes and mins right there, right? You have an absolute max at x is equal to 3, and it's 7. I mean, that's the biggest value you're going to get out of this function. And then you also have an absolute min, too, at x is equal to plus and minus the square root of 2. All right, and in those cases, the values are 0. But now let's go to the graph and make sure that we see that. We should have graphed it from the start, honestly. Let's see, new graph. All right, so f of x is equal to 1/3. And I'll switch over to the screen. I'll give you a chance to continue to look at that Word doc. Once I get it graphed, I'll switch over. Minus 2x plus 2. And we're talking about that interval, so -2 less than or equal to x less than or equal to 3. Okay, switch you over to that.
So it has two absolute mins in this?
It has got, well, let's see here, because I'm looking at it and I'm not seeing that at all. So let me make sure I said this right. What the heck's going on here? Did I do the math right? I'm saying that it's got two absolute, I mean, I'm looking at the values, right? And f of 3 should be the largest value, and then it's saying at square root of 2 and negative square root of 2, we should have minimums. X equals negative square root of 2. That's a maximum. That's not right. X is equal to square root of 2. That's a minimum there. What am I doing wrong?
Does it matter if you plug it in as the derivative?
Oh, yeah, thank you. You totally saw what I was doing. Yeah, that's the mistake I made. So I got those numbers are totally, yeah, let me switch back to that so we can see what mistake that I made.
Yeah, I remember you mentioned that about the homework.
Thank you. I didn't understand what I was doing there. All right. Why wasn't that matching up? Okay, so yeah, I totally just plugged this into f prime, right? This is f up here. So it's not as easy to do it out loud, right? You should use Desmos. Plug this into Desmos and plug those in and get them. So let's see, square root of 2 cubed. That's 2/3 square root of 2. Yeah, I'm not gonna be able to do this one in my head. So let me switch you guys back over to Desmos and I'll just plug them in there and then we'll take a look at those values. All right, so we should be calculating f of square root of 2, f of negative square root of 2. We're going to come to the same conclusion. F of negative 2 and f of 3. Why? Oh, right, that's why. Their numbers are totally different than mine altogether, right? Because I was totally wrong. I was plugging you into the wrong function. But same thing. At 3, you have your maximum. The value is 5. And you can see it. It's right here. X is equal to 3. It's sitting right there. And you can see that now, if we look at this, the smallest number out is negative 1.41, and that's at negative square root of 2. No. Sorry. Here we go. The smallest number out is at square root of 2, 0.11, right? This one right here, that matches up with this right here. And so you're seeing your absolute min is there, your absolute max is there. Notice what were these other values? Like what was f of square root of 2? F of square root of 2, sorry, f of negative square root of 2, this piece right here, it's a local max. It's a critical value and there's a chance of it being a local max or min or an absolute max or min. In this case, because of the fact that you're just looking at the outputs itself, so at these outputs itself, you can see which one is the largest one. And so this isn't the largest, but it is a critical value. And if you were to do the first derivative test, you would see a change in signs. You would see it going from positive to negative. And so then you know that this would have to be a local max. Same thing with f of negative 2. This is not a local max, though. This is not local max. This is not local min. This is not absolute max. And this is not an absolute min. Just a point. Right? The reason it's not local, and this is where some students will make this mistake, and I'll really point this out. This is not local minimum because you can't draw a circle around it where you could like draw a diameter through that circle. So imagine the graph stops at that point, and so it has no limit coming from the left-hand side, and so it can't be a local min or a local max. It just can't be local at all. You have to have something to draw around it. Like this, you could draw a circle around it, and you've got the graph going through both sides of the circle. Draw a circle around that point. It's only going through the one side of the circle, and the other side, there's nothing, right? Because the graph doesn't continue.
So it has to be like an inflection point.
It's not even. It just can't be at an endpoint. That's the more important part. It can't be at an endpoint. So, like for example, if I restricted the domain of this function from negative square root of 2 to square root of 2, this wouldn't be a local max anymore because it's an endpoint. And so then you wouldn't consider that a local max. no, it's a critical value, so it could be. Never mind, I speak wrong. That's a critical value. That's why, I mean, that's what it comes down to. Local mins and maxes, they can only occur at critical values. That's it. That's the best way of remembering it. So all the fine details that get confusing, the major point to just remember is to be a local min or a max, you must happen at a critical value. That's the best way of thinking of that. So this isn't a critical value. It's an endpoint, but it's not a critical value. So therefore, it's not possible being a local min. All right. Where are we back at the homework? All right. So what am I sharing with you guys right now? I'm sharing the web browser, right?
Yeah, right now you're sharing the textbook.
Okay. So find all the critical values that lie in that line. So there we saw that. We saw, yeah. So from the graph, determine the x values which the absolute minimum and absolute maximum occur. Then it says, how do your answers change if we instead consider the interval from -2 to +2? So if we just change this endpoint, gosh darn it, Control Z works. If I change it to 2, now it changes things a bit because f of 3 doesn't exist anymore. Look, it says it's undefined because it is. So I have to test my endpoints and the critical value. So my new endpoint is f of 2, and f of 2 I get a 0.66 out. So I've got an absolute maximum now at -2. No, at negative square root of 2 right here. 3.88 is the largest value coming out. There it is. So here's your new absolute max because we changed the domain. It also is a local max because it's a critical value and it's, you know, we used a FDT, first derivative test to see that. And we still have our absolute minimum that has not changed. It's still at positive square root of 2. But notice the endpoints are no longer in play. We test them. They are neither maximum or minimum, absolute. So they are just random, you know, they're just values that happen within. Okay. Yeah. So that's, I mean, that's the stuff that we're doing from this. So here, these are, I'm not going to go over these right now. I'm going to go over a different problem with you. But these problems right here, maybe not all of them, but for example, like A, B, C, I would, at a minimum, A, B, and C are problems you should seriously look over. Actually, I would say A, B, C, D for sure. Now, A, B, and C, I believe you should be able to do those by hand. I mean, use Desmos as well to help you, but you should be able to do a lot of that math by hand. For D, it's not that you shouldn't be able to do it. Like, I think you should be able to take the derivative of that. It's a little bit more of a complicated one outside of what we will necessarily be, you'll necessarily see from me. But like that type of problem, problem E, problem F, you know, maybe those are better problem. Actually, no, E and F, you shouldn't try at all. But like problem D is a great problem to type into Desmos and then start thinking about what those answers would be just by visually observing it. Maybe.
Will we be seeing anything like D on the homework?
D on the homework, possibly. I mean, there's actually some of the homework problems are, one of the homework problems requires you using visual confirmation of things instead of actually taking the derivative, versus another problem has you take the derivative and do the actual calculus behind it. So sometimes, you know, the functions you're working with are a little difficult, and so the derivatives itself are very detailed, but that's not what our focus is. Our focus is understanding what the derivative gives us information-wise. You know, we're not training you to be like professional derivative takers, right? That's not the goal of this. The goal is to understand the information available and how we can do it. And you come to that point in your life where there's a really tough function that you've got, find a mathematician to take that derivative for you, right? Or a program that will do that. So understanding the theory behind it, but you know, maybe the handwork of it itself, maybe not too much. I mean, I don't know even how hard it is. It's just that it's e to this little funky function up there. So it's like 2 chain rules I'm seeing happening. The problem I want to go, the other problem from this section that I really want to show you guys is this one right here. I'm going to pose the solution for that. note that these solutions are very detailed. When you click on it, it will give you a really good workup. And I'm going to do it a little bit differently than they do. So here, this is a common problem. You're going to see something like this on your homework assignment. It's less of a word problem. It's a word problem, but it's not as detailed. So it says a 20-centimeter piece of wire is cut into 2 pieces. So we got a straight piece of wire. We're going to cut it into 2 pieces. One piece is going to be used to form a square. You're just going to take that piece of metal that you cut, and you're going to shape it so that it's a square. And then the other one is going to be formed to shape a equilateral triangle. So a triangle that has 3 equal sides. That's, it's not hard to do. You take that, cut it, and then you shape that. What we want to do is we want to figure out where on that wire should we cut so that the resulting pieces that we get, when you add the 2 areas together, give you the largest possible area that you could make out of those 2 shapes added together, right? If you think about it, like if you were to use, for example, all the wiring just for the square itself, okay? The square would have, so if you've got 20 inches of wire and then your square's got 4 sides, then divide 4 into 20, and that means you'd be able to create a square that has a side length of 5, right? 5, 5, 5, 5. So the perimeter of 20. That area of that square is 25, right? That's testing, that's kind of like testing an endpoint. We're going to see that in a little bit. So that really is. Your other option, what if you used all of that wiring for your equilateral triangle instead? So you gave no length at all to the square, and it's only being used for the equilateral triangle. Well, triangle's got 3 sides, and they're all equal sides in this case. So each side is going to have length of 20 over 3, right? Each side would have length of 20 over 3. Then you have to find the area of that triangle. Area equals 1/2 base times height. But you don't know your height on that triangle. So you could form 2 right triangles and then use the not the quadratic formula, the Pythagorean theorem to figure out what that height would be. We'll do that in a little bit. And then you'd come up with some total number for that area. So those are 2 specific situations where you dedicate the wire just to one object each. That's it. And then look at those individual areas. And with is there a possibility that if we don't just do that and we share some of that wire with both objects, can we get a larger area than whatever those 2 areas would have been? So the first thing we have to do is come up with the different formulas for this. So I'm going to use their picture that they draw it out nice here. So what they go ahead and say is we need to decide what our variables mean. So what we're going to say is we're going to use x to go along with the triangle, right? So I'm going to use x amount of, what is this in centimeters? Yeah, I'm going to use x centimeters to, I'm going to cut x centimeters off. That x centimeters is going to be used to wrap around this triangle. So the perimeter of the triangle is x. And that means each side of the triangle is x over 3. Right? This has side length x over 3. This has side length x over 3. And this has side length x over 3. Because x plus x over 3 added together 3 times is equal to x. So if we used x centimeters of the wire, then how much is left? Well, we started with 20 centimeters. And we just used x centimeters for the triangle. So the square has the remaining 20 minus x centimeters left. And that's what it's going to use for the square. And so that means what is each square length side? What is the length of each side of the square? Well, it's going to be 20 minus x over 4, right? Because there's 4 sides to a square. If we know the lengths of the sides of these objects, then we can calculate their areas. So I'm gonna do it myself because the way that they do it isn't the way that I would have done it, and I don't think you would have. Let me share the Word document. All right, so let's insert new page. All right, So we're talking about the area. Let's talk about the area of the square first. All right. So area sub square. Right. That is equal to, in the area, we saw that the side length was 20 minus x divided by 4. Right? And the square, so what is it squared? What's that squared? Right? That's the area of a square, side length squared. So if your side length is 20 minus x divided by 4, then the area of this square is that formula right there. Now the area of the triangle, we can't handle that yet. All right, we need to set up Pythagorean theorem on this one. All right, so a squared, remember a squared is a squared plus b squared is equal to c squared. Right? That's what we're starting with. What do we know? We know c squared for sure. We know what c is. C is the hypotenuse. And that's every single side of that triangle is x over 3. So even the hypotenuse for your right triangle that you can create would be the x over 3. So we can say c is equal to x over 3. Therefore, c squared would be x squared over 9, right? And then we know one of those legs. If we call the base a, right? If we say the base of that equilateral triangle was length, if your a is half of that, right? You got your equilateral triangle. You draw an altitude straight down to the bottom of that triangle. It cuts. You get 2 right triangles, right? Right triangle 1, right triangle 2. Here's your equilateral triangle. This right here is A. The length of this piece, not both of these, but just the length of one of those is A. We know the length of both of these together is x over 3. So half of that is x over 6. So this is x over 6. This is x over 6. Them added together is x over 3. Right? So that we'll say that's A. So A is equal to x over 6, which is half of x over 3. So we're going to look for B. Right? So B squared is equal to C squared minus A squared. So we're talking about x squared divided by 9. That's your C squared minus A squared, which is x squared divided by 36. All right. I'm going to turn this into, actually, I don't want to skip this. I'll just, I'll rewrite it. So this becomes 4, we get a common denominator, 4 over 36. So that is equal to 3x squared over 36, which is equal to x squared over 18. Nope, 3 goes in over 12. Okay, that's b squared. So then b squared is equal to x squared over 12. So b is equal to the square root of x squared over 12. Well, the square root of x squared is x in this case, right? Because x has got to be positive. We're talking about lengths of a wire. So x has got to be positive. So the square root of x squared is just x. And the square root of 12 is 2 square roots of 3. Like that. The book is going to have it written where they rationalize the denominator. So just so we can see where theirs comes up with, they multiply both sides by top and bottom by square root of 3. So they're going to end up getting x. They're going to get square root of 3 over 6x. They're going to get square root of 3. That's 3 times 2 is 6. Square root of 3 up top. Yeah, that's what they should get. Let's see, that's what they got. Yeah, they have x square root of 3 times. Yeah, they have the same thing. All right, so that's your B. What were we doing again, right? We just did so much work. What the heck were we doing? We're trying to find the area of that equilateral triangle. And we needed to know the height, right? We know we have a base, we have a height. So your base is equal to the x over 6, right? That's the base of one of those triangles. Actually, no. We're going to use the whole thing now, right? So the base of the whole thing is over 3. And then the height all right, so height is equal to the square root of 3 over 6 x. And so then the area of your triangle is equal to 1/2 base times height. So slash c dot x over 3. Okay. And that's, so we get a 1, that's 6, that's 36. And then you have an x squared. I'll put the number out in front. Square root of 3 over 36. Dakota, get out of there. Okay, that's the area of your triangle. So let's go back to the book and see where we go from there, because what we've got now is we need to add both of those together, right? Because we're thinking about optimizing the combined area of these two. Right? I'm showing you the correct thing. Okay, great. Okay. All right. So look, we should be, yeah, we're looking at the same stuff here now, right? So they have the area of their square, they have the area of their triangle, and they're adding them together. And this is the area function. We're trying to find the maximum value that this area a of x function can take on. And so what is, if we take this function right here, and we were to plot 0, take all the values of x set equal to 0 through 20, this function is going to return the different areas that these two combined objects can give us. When x is equal to 0, what are we looking at? Well, when x is equal to 0, here is your triangle component. This is the area of your triangle. And that would have a part, that would be 0. So when in this problem, when x is equal to 0, that means we've allocated all 20 centimeters to the square. And it's giving us the area of the square just by itself. When I let x equal 20 in this problem, so a of 20, then I get an area for the triangle, but the area of the square is 0 now, which means we've allocated all 20 centimeters to the equilateral triangle. In between all that, we get different situations. So when x is equal to 1, that means we have a square that gets 19, a perimeter of 19, but the triangle only gets a perimeter of 1. When it's x is equal to 2, the perimeter of the square is 18, and the perimeter of the triangle is 2. And so we, it goes all the way up and down like that. And so, each of the objects will have its turn and having larger portions than the other. But the most important thing is one of these is going to be maximum. There's going to be some x value that we're going to get a max out. So we should look at this on Desmos because that, we can see it. So why not just jump to the solution that way, and then we'll do the calculus after the fact. All right, so a of x is equal to square root of 3 over 36 x squared. Okay, that's your triangle. And now we're going to add the rectangle area, which is 20 minus x divided by 4. And this is quantity squared. Wait a minute, is this quantity squared? Let me make sure I'm doing that right. Yeah, it is. It's quantity squared. So the 4 gets squared as well. Okay, like that. And so let's take a look at the graph itself. And we only want to know from 0 through 20. So 0 is less than or equal to x, which is less than or equal to 20. Okay. All right, here's the graph, okay? So now, are we trying to maximize or minimize? And we can ask two different questions. This question could have been posed: what's the minimum amount? What's the maximum amount of area, right? Using this material. The original problem here was to maximize, right? How should we cut the wire to maximize the total area enclosed by the square and triangle? Oh, and then it says also to minimize it. So we're going to answer both. So look at the graph. This plots the area given x. It's obvious. The best way that we can maximize our area is by setting x equal to 0. When x is equal to 0, we get the largest possible area out, which is 25. So in this problem, the best way to maximize the area is to only use the wire for the square. Don't include the equilateral triangle at all. And you'll get the maximum area. To get the minimum area using those objects and the entire length of that stuff, we can see where that occurs. It occurs at this value right wherever this point is right here, right? That's the lowest area, that's the smallest area coming out. Looks to be about 11.301, but this is where we use calculus to get the exact location of what that is. It's, yeah, I mean, you can see it's definitely greater than 10, less than 12, so it's somewhere inside there. No. So we have to take the derivative. Do the first derivative test, but not even first derivative test. You don't need to, because you see this. So what do you need to do then? Is you need to just go ahead and find the critical values. So take the first derivative, set it equal to 0, and then you'll find the exact location of where that's happening at. And so we have that function. Go back to this problem right here. Here is the derivative. Instead of me typing it out, they have it broken down. So let's just do it together this way. Take your 2, multiply it, and you get 18, right? The 2 and the 36 become 18. Square root of 3 stays the same. That 2 becomes a 1. So that's your derivative for the triangle. The derivative of this, chain rule we're going to use. So take the 2, bring it down. You keep the original function, change that 2 to a 1, and take the derivative of the inside. That derivative of the inside, do not use quotient rule. You can. It will work if you do it correctly, but there's no point. 20 minus x over 4 is the same thing as saying 20 over 4 minus x over 4. The derivative of 20 over 4 is just 0. And so you're really just taking the derivative of negative x over 4. So that's negative 1/4. So that's why this is negative 1/4. Multiply these carefully through, and they come up with this right here. This is linear. That's square root of 3 over 18 x to the first power plus 1/8 x to the first power minus 5/2. That is actually not a difficult one to solve. You can plug this into Desmos and set it equal to 0. Let's do that. That would be a good way of solving this one. But you could totally solve that one by hand. You just got to factor that x and then do some division. But if you got to that point and then you had this over 18 times x plus 1 over 8x, and then minus 5/2. Okay. All right. Set that equal to 0. Right? There it is. There's the actual location right there. Yeah, they're giving us the 11.301 again, so we could do that. The other way that you can do this, though, is you can just factor out that x. So this is square root of 3 over 18 plus 1/8. Right? That's equal to, you bring 5/2 to the other side. That's equal to 5/2. And so that means x is equal to 5/2 all divided by this mess right here. You plug that into Desmos or your calculator, and you're going to get, if you set this up correctly, which I did not, 5/2 is 2.5. So let me just do that. There you go. 2.5 divided by that is 11.3007. So this is more exact than the other one. But that's where it's happening at. And so if you cut x equal, if you give x equal to this, to the square, that's important. This goes, no, I'm sorry. No, it doesn't. X is equal to this. This is the side of your, this is the side of your triangle, right? Not the side, this is the perimeter of your triangle. And then 20 minus X is the perimeter that you would use to give to the square. And when you do that, you're going to have, what is it? All right, 20 minus this. So this would be what you would give to the square. All right. So my only word of caution on this is if you get the math down, like you've got that down, let's say, where can you go wrong still? It's interpreting the solution. So make sure you understand what the actual numbers coming out mean, and you may have to take it a little bit further. Like if this asks, how long do you need to cut the square to minimize the area? The answer would be 8.699, right? That would be the length. So it wouldn't just be the answer of 11.3 that came out, because that is referencing the perimeter of the perimeter of the triangle. Okay. All right, so that was that problem that I wanted to go over. Let me see if anyone's typed in any questions. I don't think you guys have right now. This 3.34 one is a good one because I mean, for you guys to practice, because that will give you another example of trying this one. This problem that I just did, this reminds me of question number 3 on the homework that you guys are going to work on, right? So when you read question 3, it's very open-ended, okay? It's just a statement. And this is the problem you should be thinking about, because this problem is done in a similar way. It's not exactly the same, but the concept of having to do a little bit of work in the beginning and then just using derivatives, plotting it to try and find out what the correct answer would be for that problem. Right. Yeah, and then there's a couple problems here at the end. They don't have many for this. This was strange. I was looking at this ahead of time. They have 3 problems or 4 problems, but none of them are interactive, and they're very mathematical looking in nature. So the ones that would be really good to practice on these here. One would be a good one for you guys to practice. 2 would be pretty good. Again, just, some of these get a little bit challenging. This one here, you have a lot of different values that they're variables. They're not new numbers. Like this is an A and not an actual number. So if you're finding that's too hard, maybe change it to an actual number and go from there. Set A equal to 1 and see what happens. Set A equal to 10. See if things change. And then see if you can just say, all right, I want to set it as a number. I'll just use it as a variable. And can I do that now? Those will be things to think about. 3 is another good one. 4 is a good one too, because it's a sine trig function, so you know a bit about how that would naturally look. So you should know, that it's got ups and downs and it's cyclic like that. And then this will give you some practice on those little intervals. But use Desmos throughout. I'm going to continue to let you to use Desmos wherever possible. And you're going to see for your project as well coming up that's going to happen. You guys have any questions about this stuff or about, because those are the things that I want to show you. But do you have questions about the project or anything else related to whatever's going on?
Would you recommend that we wait until the next class to start this homework?
No, you could actually start this one for sure. Definitely.
Okay.
Actually, yeah, no, I'd say literally all the problems on there at this point, you totally should be able to start doing them.
All right.
Okay. Yeah. I wanted to give you, it's the holiday, holiday, all different religions and stuff like that right now. So, give you the flexibility and the time to, if this week works better for you, like if you got time now, but the rest of this week is going to be terrible for you, get a head start. Is the only thing you don't want to leave these to last minute. That's for sure. Right.
Right.
Because they each will require, you'll have to think about them. Okay. Any other questions? I hope you guys are enjoying this.
And what were your hours again? Your 9 o'clock?
What's that?
What days are you available at 9 o'clock?
Oh, Monday, Tuesdays, Thursdays. I'm on every Monday, Tuesday, Thursday at 9 a.m. on this site.
Okay.
Okay. And if you need some other time too or something like that, just email me. We could either meet up on Zoom or I can just answer questions that, through email. Just stay motivated. Remember, I was looking at it. We still have 4 weeks of class, right? We have the month of April, actually, or I guess how long is April? I think it's 5 weeks, right? Something like that. All right, so we got 3 weeks left. No, 4. Counting this week, we have 4 weeks of class left. There's still a lot of information that you're going to be learning and stuff like that, and you got to try and stay caught up with all of this. If you are finding that none of this makes sense, then you need to let me know that through an email. But be very specific. Say this concept doesn't make sense. You can't say that everything doesn't make sense. I mean, I can give you some advice on that, but it's not going to be as helpful as if you were very specific. Say this chapter or the first derivative test or taking a derivative. I'm still stuck on that because I can give you videos at least. I mean, there's lots of stuff. Maybe I'll give you a Khan Academy one, or maybe I'm going to give you something even better. I mean, MIT and all the upper level colleges out there, they publish almost every single lecture that they have. So there's lots of stuff for me to share. The way I say it might not be the best way. Maybe you will learn it from hearing it from someone else, or just hearing it over and over again from different people. It might help. So, but you got to communicate this stuff with me and stay on top of this. There's only a couple things left. I mean, there's only going to be like maybe 1 or 2 quizzes left. There's definitely 2 quizzes left. There's not just one. So I'm thinking that there's 2 quizzes left. Your project, which is worth 10% of your grade, and it's going to take up time. Make sure you really look at that once I give out the groups and you guys start communicating right away. College really likes this the math department really likes this project being given. So it's important to them. And I know the other math classes, when I was a student at Montclair, every course I took, there was always some type of project. I mean, it was graduate school, so maybe it might be a little bit different for undergrad, but I can't imagine that it's much. And the math department likes to give out their projects. This is a really good one where you see calculus at its real use. So, and the way that you guys will be using it as, science. So stay on top of that. And then the final exam, as we get closer to it, I will give you, I haven't decided exactly what I'm going to do. It may just be like the midterm. There's a really good chance that if it is like the midterm, this time it's going to be at more of an assigned time where we can all come on Zoom and, you'll take it while you're on Zoom, but through Canvas or something like that, just for the integrity of the course. Or it could be some individual project or a take-home exam type thing, or it could be like the midterm where you have the full day. But I'm really thinking about all of those things. So if it was a thing where we were to get together all at the same exact time, I would do it at our normally assigned real-world time that we used to have.
So I just had a quiz in a different class, and she wanted us to use Zoom and also use a lockdown browser. But
I wouldn't do the lockdown browser. I think Zoom
Okay.
is fine enough for me. Yeah.
Because
You guys-
Zoom
I
wasn't
want you
working
guys
with the
to use
lockdown
Desmos.
browser.
I want you to use the open book. The thing I don't want you to do is to be communicating with each other during it. You know what I mean?
Right.
So, there's really, it's all comes down to trust, but yeah.
And are you thinking it's going to be cumulative?
Oh, it will be,
Or-
yeah, it's definitely gonna be cumulative. I honestly believe we've learned the most of the material already. So you've already learned the majority of Calc 1. The only thing left is a couple of other applications of derivatives. You're not learning new derivatives, like the derivatives are done. And then integrals. And you only get an introduction really into integrals. You won't get deep into that. That's more Calc 2. That's where Calc 2 starts off at. So you've gotten all the derivatives was the main method, like the main theories that you've got. Now it's just applications of it, which is the most useful stuff for you guys. All right. If you have other questions, you can feel free to ask them. You can hang out while I drink my seltzer water.
And if we have more general questions, would you rather them be on the discussion page?
Yeah. Actually, yeah. I do check it. No one's been using it. You should. Yeah, you should. I mean, if you've got a math question, post it on there if you want to help everyone else out. Because I'm going to respond on there. And I'll get it just like it will come to me as an email, even if you post it on there. So I'll get it immediately. And then tomorrow, I think I don't know what my announcement said. I'll read it again. What I announced at some point, I'm going to review the midterm exam if anyone is interested. I think it's tomorrow at some time. If not, it's point this week at some time. I'll be there. So I'm just making sure that you're aware of it. Just checking the announcement for it. Will that review be recorded? Sure. Yeah, why not? Who's this I think this one's being recorded. Is this one being recorded right now? Might be being recorded too. If it is, I'll share this one. Oh, great. Yeah.
Yeah, it's recording.
You have plenty, like just an infinite amount of problems that you can do. Pick any quadratic equation that you can think of. Pick any cubic equation that you can think of. If you start taking those derivatives and doing the first derivative tests and stuff like that, you got a lot to practice if that's the issue itself. Okay. Any other questions?
That's it from me.
All right. Thank you very much for showing up. Did you let it? Is everyone actually here? Or they?
We got a part of the class, I
They
guess.
just signed in. This is why it's not mandatory because I don't care. I mean, if you're here, I would assume that you're actually paying attention. All right, guys. Have a good one. And if there's nothing else, I'm gonna sign out. All right.
All right, take care. Enjoy the weather.
All right. Thank you. You too. Bye, guys.
See you later.
Bye.